This example problem is from the end of chapter 3 in your physics book. We're looking at problem number 72. A stone that starts from rest is in free fall for 8.0 seconds. For question A, we want to know the velocity of the stone after the 8 seconds. And then for question B, we'll look at what is the stone's displacement during that 8-second period. What do we know here? There's only one piece of numerical information that's stated clearly, but we have some ways to figure out other information. For example, we're told that the stone starts from rest. This is a way of telling us that our initial velocity is 0. Rest means not moving. And we have our time, 8 seconds. And then we're told that the stone is in free fall. This means that the object is under the influence of gravity and only gravity. So we're ignoring air resistance, no other resisting forces. It's not being jet propelled up or down in any way. It's simply being accelerated by gravity. And near the surface of the Earth, gravity accelerates things at a rate of 9.81 meters per second squared. You'll notice I put a negative sign in front of it. So this stone is moving along a vertical axis. And we have to choose whether up is going to be positive or whether up is going to be negative. So I'm treating up as positive, so things that are in a downward direction, like acceleration due to gravity, will get a negative sign to indicate that direction. Acceleration, velocity, both vectors. We need to think about direction here. For question A, we want to know the velocity of the stone after 8 seconds. So we're looking for the final velocity. And we also, for question B, want to know the displacement. Gravity, as long as we're near the surface of the Earth, it provides a constant acceleration, so we can choose from one of our 4 kinematic equations. We know our initial velocity, our time, and our acceleration, and we want our final velocity. So take a look at these for a moment and see if you can figure out which equation we want to use. Okay, hopefully you chose this one. This is the thing we want. We know this, and we know the time. So let's plug in our data. Our initial velocity is 0 because we start from rest. Our acceleration is negative 9.81 meters per second squared because it's gravity. And we're told that our time interval is 8 seconds. So let's take a look at our units. This second cancels out with one of these, so we're going to be left with meters per second. This makes sense because we're looking for a velocity. Now let's multiply our numbers. We get negative 78.48 meters per second. That's our velocity, but we're not done yet. What do we need to do? We have 3 significant figures for gravitational acceleration, and we have 2 significant figures for our time. And we're multiplying, so our answer can only have 2 significant figures. Our answer cannot be more precise than our least precise input information. So 7 will be my first significant figure. 8 will be my second, and I have to decide, am I rounding it up to 9 or am I keeping it? This is less than 5, so I'm going to keep the 8. And my final velocity is 78 meters per second for part A. So let's move that over to our list of known information, and we get our kinematic equations back because we're going to look for the displacement now. Which equation can we use? Well, let's start from the top. xf and xi, I want this. I know my initial velocity, I know my time, I know my acceleration, and we know the time. So that could work. The second equation doesn't have anything about position, so it's not going to help us out. Our third equation, this is what we're looking for. We now know our final velocity, and we still know our initial and our time, so we could use the third equation. And the fourth one, we know our velocities, we know our acceleration, and we're looking for our displacement. So we have a choice. We could use either the first, the third, or the fourth equation. Which one? It's really up to you. You pick the one that looks the easiest for you. I'm going to go with the first one because we haven't looked at it yet. So I want the displacement, xf minus xi. In this equation, I have xf by itself. I'm going to subtract my initial position from both sides so I get the displacement on the left side of the equation. Now I'm going to look at my known data here that I can plug in. That term is going to go away because my initial velocity is 0. Now I can sub in my acceleration and my time. I'm going to square my time. Notice that the exponent is outside of the parentheses. I need to square both the quantity, 8, and the unit, seconds. So 8 squared is 64. Seconds squared is seconds squared. What's going to happen with my units here? I have seconds squared, and I have seconds squared in the denominator down here. So those units will cancel out. Now I'll multiply my gravity and my time squared, and I get a displacement of negative 627.84 meters. Back to our significant figures. How many here? 1, 2, 3. How many here? Only 2, right? And it was 2 here. So I need to round this. I'm going to keep the 6, and I'm going to keep this digit, but does it go up or down? Well, it's followed by a 7, so this needs to go up, and I'm going to put it in scientific notation. Negative 6.3 times 10 to the 2 meters for my displacement.